Hi, in this video we are going to see what happens if we replace the Schottky diode of our buck converter with another type of diode. In particular, we are going to consider this diode we have here. The type of this diode is called fast recovery. One of the first changes we will have to perform in order to reach the target output voltage is to increase the duty cycle. And basically it indicates that with the new diode we will have higher power losses. So here we have a comparison between the main parameters of both diodes according to the datasheets. Here we have the Schottky diode and here we have the new fast recovery diode. The manufacturer is the same in both cases. The breakdown voltage is higher in the case of the fast recovery diode, but you can find in internet another fast recovery diode with a breakdown voltage closer to this one, but the conclusions that we are going to obtain here are the same. The maximum continuous forward current is very similar. The maximum instantaneous forward current is also very similar, a little bit higher in this case. And it's important to note that the forward voltage drop is much higher in the case of the fast recovery diode. And moreover, that voltage is evaluated at a smaller current level. Here we have 10 amps, here we have 30 amps. If you evaluate this voltage at this current, this voltage will be higher. So one of the conclusions that we are going to obtain in this video is that the fast recovery diode has higher forward voltage drop and it will be translated into higher conduction losses. The size is very similar, and well, as you can see, I don't include information about the reverse recovery process. If you check the datasheet, you will find information about this effect, but that information is incomplete because that process depends on a lot of parameters. For instance, it depends on the current. So the problem is that each manufacturer evaluates the effect at a different current level, and probably they change the current level from one device to another device. So in summary, you cannot do or perform a fair comparison between diodes. So what we are going to do is evaluate it in terms of simulation. So as we will see, the reverse recovery process is not as good as in the case of the Schottky diode. So the question is why we have in that case fast recovery diodes, because if the Schottky diode is better in terms of conduction and in terms of switching, why we have fast recovery diodes? Well, the answer is that in general fast recovery diodes are available for higher voltage levels, and perhaps you have an application where you don't have, or you don't have the option to choose a Schottky diode. This is not our case because we work in very low voltage levels, but well, with this video we want to explore the conclusions we get when we change the diode, and in this way we know what we have to do in other scenarios. Well, so let's evaluate some of these parameters in LTspice. Here we are evaluating the forward voltage drop across the diode. So basically we measure the voltage in this way, and what we want to do is to see what is the forward voltage drop when the device obviously is on. So we have an interval in which the diode is on in our buck converter, and in red you have the results for the Schottky diode, and in green you see the results for the fast recovery diode. As you can see, the forward voltage drop is smaller in the case of the Schottky diode, and in the case of the fast recovery is close to the value offered in the datasheet. So in this way, this conclusion be similar to the information we have in the datasheet. Let's talk about the reverse recovery current waveform. So in this case, what we are going to do is to evaluate this current during the turn off of the diode, which in other words is during the turn on of the MOSFET. So here we have the results of the Schottky diode. We already talked about this result in previous videos. As you can see, it's a very short interval, only 30 nanoseconds. Our switching period is 10 microseconds. And we focus on the turn off because, as you can see, here we have the inductor current. We turn on the MOSFET, so the current through the diode falls. Here we have 0 amps, but the current continues in the opposite direction. Here we have the reverse recovery process with this negative current peak, and here the switching process finishes because we have 0 amps. So here the diode is completely off. Let's see the same for the case of the fast recovery diode. Note that this axis is very different to this one. Here we have minus 10 amps, here we have minus 100 amps. So as you can see, the reverse recovery process is not as good as in the case of the Schottky diode. Here we have the inductor current, which is the same we have here. We turn off the diode, the current falls, here we have 0, the reverse recovery process, and here we have 0. So the negative current peak is much higher because it's almost 100 amps. What is the impact of this higher current peak? Well, the impact is that we will have more power losses on the MOSFET turn-on process, because basically the MOSFET must drive this current peak during the turn-on, as we explained in previous videos. Well, here we have the same, the reverse recovery current waveform, but in this case we see the two waveforms in the same figure, in order to clearly see that the Schottky diode is much faster than the fast recovery diode. Okay, here we have the reverse recovery of the Schottky diode, and here we have the reverse recovery of the fast recovery diode. Well, what is the impact on power losses? Here we have power losses as a function of design 1 and design 2. In blue we have the conduction losses of the MOSFET, in green we have the switching losses of the MOSFET, in red we have essentially the losses of the diode, which are mainly the conduction losses, and in gray we have the inductor losses, which is the power losses we have in that our simple model with that small resistor in series with the ideal inductance. So in the previous design, the total power losses were 6.6. We already talked about this result. And in the new design, with the fast recovery diode, is 11.6. Where we have the increase of those power losses? Well, first of all, we have an important increase in terms of MOSFET switching losses. Here we have 0.6 extra watts of power consumption in the turn-on of the MOSFET due to the higher reverse recovery of the fast recovery diode. And then we have another important increase in power losses in the case of the diode conduction losses, because as we saw, the forward voltage drop in the case of the fast recovery diode is much higher than in the case of the Schottky diode. So at the end here we have like 4.4 extra power consumption. So with this video we have seen what is the impact of changing the diode type in our buck converter design. So the conclusion is that Schottky diodes are the correct selection for our case, taking into account the voltage levels we consider, but perhaps in another scenario we don't have Schottky diodes for a higher voltage level, and we have to use another type of diode. So with this, we finish with the video. See you